Hello, welcome in the 13th lecture of my course Convective Heat Transfer. In our last lecture we have discussed about slug flow, okay, where velocity was almost constant, okay. Hydrodynamically the boundary layer is not developed. Here we will be considering about thermally and hydrodynamically developed flow. That means hydrodynamic boundary layer is already developed, okay. That too, in this lecture we will be considering uniform heat flux. So, that means the pipe is actually wrapped up with some coil, electric coil let us say, or heater coil let us say, which is supplying uniform heat flux, okay. So, let me first tell you that what we will be covering in this lecture. In this lecture we will be first deriving conclusions for thermally fully developed flow in terms of the boundary conditions. Then we will be discussing or we will be reducing the energy equation into non-dimensional form for uniform heat flux case. So, we will be considering only the uniform heat flux case over here in this lecture. In next lecture we will be discussing about uniform temperature case. Solve the energy equation for obtaining temperature profile in terms of bulk temperature, and lastly determine the Nusselt number for thermally and hydrodynamically fully developed forced convection over flat plate having constant heat flux, okay. So, let me start with the topic. So, as we are only interested in thermally fully developed region, so as it is thermally fully developed, so the heat transfer coefficient will not change with respect to time, with respect to radius at least. So, Hz we will be keeping as constant, okay. Hz is constant means as it is fully developed it will not change with respect to z. So, Hz is constant, okay. As Hz is constant, let me see that what are the other quantities. For example, bulk temperature, okay. Bulk temperature is obviously the integration over the radial plane. So, here you can see this will definitely not depend on the radius, so it is a function of z only, okay. On the other hand, wall temperature obviously it will not depend on the radial plane, okay. It will be only at, it is only valid at R naught, which is the tube diameter, tube radius, okay. So, T is actually a function of Z. So, here we are considering TW is actually a function of Z, okay. So, both we have got as a function of Z, and Hz is actually constant for thermally fully developed region, okay. Next, let us see by definition this heat transfer coefficient H is nothing but Q by TW minus TB, okay, wall temperature minus the bulk temperature, okay. So, here you see Q can be written as K del T del R at R equals to R naught, that means at the wall, okay. So, here we get K del T del R at R equals to R naught divided by TW minus TB. Now, here you see TW and TB both are function of Z. So, what we can do, this term we can take inside the del del R term. So, there we have done del del R of T by TW minus TB, because this TW minus TB is actually not a function of R, okay. So, as constant that can be taken inside. So, actually this T by TW minus TB now it is becoming a function of R, as T is function of R. So, this whole term is becoming function of R, okay. And as we have to make Hz equals to constant, so obviously this has to be a function of R only. We will be putting the derivative and then putting the limit R equals to R bar, R equals to R naught, and ultimately this Hz will become a constant, okay. So, let us define non-dimensional number like this, phi is equals to T minus TW by TB minus TW, okay. So, if you remember in our last lecture we have considered Ti minus TW, here let us define with TB minus TW, okay. Why? Because we want to make this phi only as a function of R, okay. So, this T by TB minus TW is actually a function of R in the thermally fully developed region, okay. Now, if we define this phi in this fashion, then definitely phi W at wall the value of phi will become 0, because T becomes TW, okay. Then let us see how the derivative looks like. So, T as per the definition of phi becomes TW plus phi into TB minus TW. Here I have showed the dependencies based on the R and Z coordinate for different parts of this equation. Now if we go for the derivative with respect to r first, okay, if we go for the derivative with respect to r first, this is function of z, we need not to do, this will be also constant, this is not a function of r, here it will be only becoming the derivative. So only you see this is remaining as constant and this is becoming del phi del r, okay. And now if we put r equals to r bar by r naught, then this r bar needs to be transferred to r with 1 by r naught multiplier with this term, okay. So del t del r bar becomes this one, okay. If we proceed further for the heat transfer coefficient, so for the heat transfer, from the heat transfer coefficient we can see now this becomes, as per the definition, as per the non-dimensionalization of the temperature, it becomes actually minus k by r naught del phi by del r, okay. So del t by del r, okay, you can get from here del t by del r is actually del phi by del r multiplied by this term, okay. So here we are having already Tw by minus Tb, Tw minus Tb, and here Tw minus Tb will be cancelling out with a minus sign, okay. So this minus sign, then k by r naught del phi by del r at 1 z, this 1 is nothing but r equals to r naught, okay. R equals to r naught means r bar equals to r naught means r equals to 1. Okay, then if we go further for evaluation of Nusselt number, which is nothing but h d by k, h into 2 r naught by k, then from this equation we get Nusselt number is nothing but minus 2 of del phi del r at 1 comma z, okay. Now let us see for thermally and hydrodynamically developed flow with uniform heat flux, which we are supposed to discuss in this lecture. For that case, we definitely, as it is fully developed, u and v will be 0, okay. So my equation will be turning into this one. In the left hand side we are having the convection, but this time W is not a constant, and in the right hand side we are having the conduction terms, okay. Azimuthal conduction has been neglected. Now let us proceed further for constant heat flux case. So if the heat flux is constant, and as it is fully developed, H is already constant, then we can get obviously Tw minus Tb needs to be constant, okay. So here Q is constant, H is constant, so obviously it will be constant. Now if this is the case, I can show the temperature profile in this fashion. Let us say this is the z axial direction of the tube, and here I try to plot the T. So after this entrance length, that means the thermally developed region, you can find out, though due to supply of the heat flux, temperature, bulk temperature is changing, as well as the wall temperature will be changing, keeping the gap always constant. Tw minus Tb is always constant, okay. So we find out from here, as it is constant, so del ddz of Tw will be obviously ddz of Tb, okay. ddz of Tw is equals to ddz of Tb. Let us proceed further. Here let us do the derivative of this temperature in form of phi with respect to z. So del t del z will remain, here you see del t ddz of Tw, because this is a constant term now we have proved over here, and phi r is not dependent on z. So we get del z of T is nothing but ddz of Tw, and here we have shown that ddz of Tw is nothing but ddz of Tb. So ultimately ddz of T becomes ddz of Tb, okay. Now let us try to do little bit of balance of energy from convection and whatever heat we have supplied from there. So let us say m dot is the mass attached with the pipe wall, so that is taking the heat from the pipe. So m dot into Cp into dTb is equals to Q into 2 pi r into dz is the area through which the heat is being supplied. 2 pi r naught is the perimeter multiplied by dz in which the heating coil is wrapped up. So if we do this kind of balance, then we can find out dTb by dz is becoming 2 pi r naught Q by m dot into Cp. Here you see in the right hand side all terms are constant, so I can write down dTb by dz equals to constant. As dTb by dz equals to constant, then definitely del t del z becomes constant. So del t del z is constant over here, okay, because we have already proved del t del z is nothing but dTb dz, okay. So as this is constant, definitely this term will remain constant, and if this is constant, second derivative of t over z will be obviously equals to 0. So that means we can obviously neglect axial conduction in case of thermally fully developed region. So in the equation, last term we have dropped this axial conduction term, we have dropped and tried to non-dimensionalize that one with respect to W equals to W bar by W bar average. Okay, so as a result here W bar average came. Okay, and we tried to convert the phi to theta, sorry, we convert the t to phi, and we have written actually del z of t to del z of tb, okay, which we have already proved. So after little bit of side changing, we can find out that whenever we convert this r bar to r naught square also comes out, because we have considered r is nothing but r bar by r naught. Okay. Now little bit simplification if you do, then del square phi del r square plus 1 by r del phi del r is becoming W average r square by alpha dTb dz into 1 by Tb minus Tw into W. Okay. So if we further do the simplifications, then we will be finding out that we are having over here 2 r naught by k into h into W. Okay, where this 2 r naught h by k is nothing but your Nusselt number. Okay, so this becomes nothing but your Nusselt number. Here one minus sign is missing, so this is becoming minus Nusselt number into W. So my equation turns out to be this one, del square phi del r square plus 1 by r del phi del r equals to minus Nusselt number into W. Okay, where this W is nothing but your parabolic profile, Hagen-Poiseuille flow we are considering. So this is nothing but W bar is like this, so W is becoming 2 into 1 minus r square. Okay. So my final equation, once I put the value of W as 2 into 1 minus r square, this is my equation. Let us also see the boundary conditions. So the boundary conditions are like this: at r equals to 0, definitely it needs to be bounded, so del phi del r equals to 0. At r equals to 1, phi equals to 0, that means at the wall. Okay, here r equals to 1, del phi del r equals to minus Nusselt number by 2. This we have already proved a few slides back. Here we have proved that at r equals to 1, del phi del r is nothing but minus Nusselt number by 2. Okay, so that will be also coming as one boundary condition of my equations. Okay. So this is one equation at wall because we have already proved this one. Okay. Next, let us try to see what is this value of phi b. Already we have defined phi as t minus Tw by Tb minus Tw. So phi b will be obviously Tb minus Tw by Tb minus Tw, which is nothing but equals to 1. Okay, from the concept of phi b, which we have discussed in 11th lecture, we can write down that phi b is nothing but 0 to 1 W phi r dr 2 divided by 0 to 1 W r dr. Okay. Now if this is equals to 1, then what we can write down, as we know the profile of W, which is nothing but 2 into 1 minus r square, this integration is very simple, which gives me nothing but equals to 2. Okay, so nothing but equals to half, sorry, nothing but equals to half. So this becomes 0 to 1 W phi r dr is equals to half. Okay. Next, let us try to solve this equation. To simplify it further, let us consider that phi is equals to nothing but Nusselt number into f. Okay. So if we consider that, my equation turns out to be like this, cancelling Nusselt number from both the sides, as we have considered f equals to Nusselt number, f equals to phi by Nusselt number. So f will be actually phi will be actually Nusselt number into phi. So Nusselt number can be cancelled from both sides. So it becomes little bit simplistic in nature. Corresponding boundary conditions are like this. This is at the center of the tube, axis of the tube. This is at the wall, and this is also at the wall. Coming from the Nusselt number condition. Okay, this condition. Here also if you put phi is equals to Nusselt number into f, then this Nusselt number will be cancelling from both sides. Okay. So these are the boundary conditions. Let us now try to see the solution. This solution is now becoming simple. So if you do it little bit of change of order, so this becomes ddr of r df dr equals to minus 2 into r minus r cube, okay, after once integration, okay. So no, not after once integration, multiplication by r, okay. If you do the multiplication by r, then this comes out to be like this, okay. Then let us go for the integration now. So after integration, one step it will be involving one constant C1, okay, which can be found out from the boundary condition, okay, at r equals to 0, df dr equals to 0. So from there we can find out C1 is also equals to 0. If we do one step further, the integration, then we will be finding out f is becoming 1 by 2 r to the power 4 by 4 minus r square by 2 plus C2. Okay. This can be also found out by putting this boundary condition at r equals to 1, f equals to 0. So C2 gives 3 by 8. Okay. So finally the f becomes 1 by 8 into 3 minus 4 r square plus r to the power 4. Let us now try to find out the Nusselt number. As per our consideration, Nusselt number will be obviously phi by f, because we have considered phi equals to f into Nusselt number. So this Nusselt number is phi by f. Now this can be written as 0 to 1 r w phi dr divided by 0 to 1 r w f dr. Okay. Now 0 to 1 r w phi dr, already we have found out the value as half over here. Over here we have found out the value as half. We have found out the value as half over here. Okay, 0 to 1 w phi r dr is equals to half. So that we can put obviously in that equation to get that 0 to 1 r w f dr is equals to what is the value in terms of Nusselt number, 1 by Nusselt number. Okay. So now let us try to find out what is the value of this integration, as we know already the functional nature of f. So what we can put, r f w is nothing but 2 into r into 1 minus r square multiplied by the f. So this f we have put over here. Little bit of algebra if you do, it will be becoming a polynomial of r. If we integrate from 0 to 1, then it will be giving you 11 by 96. Okay. So further, if we try to find out what is the Nusselt number, because we know that Nusselt number is nothing but half 0 to 1 r w f dr, so that 0 to 1 r w f dr we have found out 11 by 96. So this is half by 11 by 96, and it comes out to be 4.3636. Okay. So we have found out Nusselt number in this fashion. So as we know the Nusselt number, so obviously we can find out what is the value of phi, which is nothing but Nusselt number into f. Okay. So Nusselt number already we have found out as 48 by 11, so that we have put over here in front of the f. So this was actually f, which we have already found out. So in this way we have actually calculated the temperature profile, okay, which is dependent on the radius, as well as we have found out the Nusselt number. Okay. So let us see what we have actually understood in this lecture. In this lecture we have actually discussed the governing equation for thermally and hydrodynamically fully developed. Okay. So here this is very important, fully developed forced convection over flat plate having constant heat flux case. We have seen that the equation comes out to be del square phi del r square plus 1 by r del phi del r is equals to minus 2 Nusselt number into 1 minus r square. Okay. The boundary conditions we have established as at r equals to 0 del phi del r equals to 0, and at r equals to 1 phi equals to 0. Okay. Also we have seen that at wall it can be found out that del phi del r will be obviously minus Nusselt number by 2. This we have proved from the equations, okay, at the beginning. Because we have understood that Nusselt number is nothing but minus 2 del phi del r at r equals to r naught comma z. Okay. and whenever we have tried to find out the Nusselt number and non-dimensional radial distribution of temperature profile, we have actually obtained Nusselt number comes out to be 4.3636, and your temperature distribution becomes 48 by 11 into 3 by 8 minus r square by 2 plus r to the power 4 by 8. Okay. So, all these things we have found out for thermally and hydrodynamically fully developed forced convection. Okay. Here probably this is mistake, this is not our flat plate, this is convection inside a tube having constant heat flux. Okay. Next, let me test your understanding what you have got in this lecture. So, as usual we are having 3 questions. So, first one, in thermally fully developed region which quantity remains constant. So, as it is thermally fully developed region, so we have 4 answers over here. First one is H, second one is actually TW minus TB, third one you can say both, and fourth one we are saying none. So, either you have to choose whether H or TW minus TB or both or none of this H and TW minus TB. So, obviously you have understood this, we have elaborately discussed in this lecture. The correct answer is obviously H. H remains constant for thermally fully developed region. Okay. Whenever heat flux remains constant, then some other features also comes into picture, but only for thermally fully developed region only H will be remaining constant. Okay. Next question is related to this one only. In thermally fully developed region with constant heat flux, now we are implying this extra condition, with constant heat flux which quantity remains constant. Okay. So, obviously as it is thermally fully developed region, H will remain constant, and due to this constant wall heat flux we have to find out something more. Let us see the options. Options are more or less same, H, TW minus TB, both and none. So, here obviously you can find out that we have proved that in case of constant heat flux and thermally fully developed region, TW minus TB is also constant. So, the correct answer is both H as well as TW minus TB remains constant. Okay. The last question is, in thermally fully developed region with constant heat flux, value of Nusselt number is 3.657, 4.3636, 5.7831 or none. Okay. So, this we have elaborately discussed and found out what is the Nusselt number. So, obviously the answer is 4.3636. Okay. So, with this I am ending this lecture. In our next lecture we will be discussing about thermally and hydrodynamically developed flow, but this time we will be considering uniform wall temperature. In this lecture we have considered uniform heat flux, but here we will be considering uniform wall temperature. Regarding this lecture, if you are having any query, please do not forget to post it in our discussion forum. Thank you.